Okay.
Okay.
Sorry.
Don't worry.
Okay, very silent.
So yes,
Okay. Yes.
it's okay.
Okay. And then the third part is also related to the peril insurance area we're working on, is to try to incorporate the impact of climate change to local rainfall pathway. So in today's, I will focus on the convective storm nowcasting one, some work in that area, and also in the how the potential solution to incorporate climate change impact to rainfall modeling. And for the RA2PW, this project is kind of the it's related to both the monitoring and also the convective storm nowcasting part. Okay, a quick overview about nowcasting, because probably not everyone is familiar with this area. So basically, there are two main sources to conduct nowcasting. Is to forecast rainfall in the next few hours. It's called nowcasting. And two sources. One is numerical weather prediction, and another one is radar-based nowcasting. Okay. In the past 10 years, we can see a significant improvement in NWP. However, NWP method require a lot of computational resources. Okay, and although they can provide quite okay performance in terms of longer lead time, in very short lead time, in the first maybe up to 6 hours or 5 hours, this kind of lead time, radar-based nowcasting usually still give higher forecast skill. Okay, and the most important thing is you just need a very standard workstation PC. You can run radar-based nowcasting, so it's very cost-effective. So today's method we developed are all based on radar-based nowcasting. Okay, before we look into the techniques, I think there's three key challenges or very important points we need to keep in mind when we talk about rainfall nowcasting or rainfall or spatial temporal rainfall modeling. The first thing is the variation in rainfall actually include two parts. The first part is the one result by advection. That means the movement of your storm, the movement of your rainfall field. But the second part is evolution. That is, during it move, the rainfall intensity, for example, or rainfall's property also vary with time. Okay, so for the radar-based nowcasting, very often we only consider advection and then we ignore the evolution. Okay, so that's also why the forecast skill decrease quickly. Actually, you have the chance, if you consider that, you have chance to increase your forecast lead time. Okay, and then another thing is the rainfall spatial temporal features. They are not independent from each other. You need to model them together, and it will give better results. Okay, and also different behavior at different scales really matters. Okay, that also need to keep in mind. So for the radar-based nowcasting, we can briefly, different method we can briefly categorize them into two types. One is called field-based nowcasting. Okay, it's used by many national weather services. Okay, the idea is they look at the current and they look at the current field, rainfall field from current several time steps, so they can derive the movement between these radar images, and then you can assume it continue with similar movement to extrapolate what's going to happen. So in this sense, computer vision play a very important role here to help you to, from two consecutive radar image, to derive the field of motion or field of movement. Okay, and the most kind of state-of-art method based on this is called STEPS. I think you probably heard about this STEPS named several times. It's also based on similar idea. However, it did in a more kind of neat way. Is it first separate your radar image according use a fast Fourier transform to separate their rainfall feature at different spatial scale. And then so for different spatial scale, they have different forecast lead time. Okay, so for example, for the very coarse one, actually they have longer lead time. And then for the very fine one, their life cycle is very short, so lead time very short, and then to combine them. Okay, so this is a very iconic method because it really takes into account the spatial temporal relationship inside rainfall and also consider account for the scales. Okay, and then the second method is the object-based nowcasting. So instead of modeling the entire field, how it moves, for object-based, it first identify rain cells from radar image at each time step, and then try to associate cells from different time steps to identify, okay, this cell will move to this location in the next time step. It's called object-based. And this method is very effective for convective storm. Because convective storm, they have their clustering nature. So they just, so there's a very obvious object, or we call it rainfall cells inside radar image. Okay, it performed quite well. And one of the most famous methods is called Titan. It's called Titan. So basically, it provides algorithm to help you to identify these cells and also to associate cells from different time steps. However, there's a very big research gap in object-based nowcasting. Is that it only considers the movement. There's really no methods here, or very, very limited number of methods here try to incorporate evolution inside this kind of model. Okay, so so in my research team, in terms of rainfall nowcasting, we work on both methods. Okay, in terms of, for example, in terms of field-based nowcasting, we replicate one of the most kind of the frontier method called DGMR. Is a nowcasting method developed by DeepMind, this company. If you don't know about DeepMind, is a company that developed the AlphaGo, the AlphaZero, that's defeat the world #1 Go player. Okay, so they also in 2021 or 2022, they proposed a method called DGMR. So they are one of the pioneer in using GAN, this technique, okay, to improve rainfall nowcasting. So you can see the difference here. So the left one is a ground truth, and this one is steps, okay, the state of art with non-UI method. And before DGMR, Google or some other company try to use UNet or MapNet to do this nowcasting, and you can see they quickly lose the detail. They quickly lose the detail, and then DGMR showed up with their model. They can keep better about these details. Okay, and the right hand side is their model is quite complicated. I'm not going to detail here. Actually, I'm going to explain this in August lecture on Friday. how this thing work and what it represents. A few words is they really take into account spatial temporal relationship, and they really consider the spatial temporal scales, their interdependency. Okay, so that's why they outperform others. They outperform UNet, outperform MapNet. And then this is just a framework of GAN. I'm not going to detail here. So just let you know, if you're interested in this model, we open source it, because the original DGMR, they didn't provide their source code. So we actually spent a lot of time to look for not just their paper, also some of the authors' previous works to finally we can replicate this method. Okay. Also, we developed some strategy to train this model. Because in DeepMind, they can use Google's facility to train this model, but we don't have that facility. So we also prepare a lot of kind of memory control way to train this model. Okay, so here is GitHub, and it's fully open source. So you're welcome. If you want to use it, you can use it. And currently, the model was trained with UK's data. Okay, so if you want, you need to prepare your own, for example, data in mutual funds, for example, you can use it. Okay, and then here just to show you that from DGMR's model, when they consider a GAN structure, the one in the middle, you can see with with forecast lead time, more details can be retained. More details can be retained. Okay, so after this work, you can see there are many new methods all start to use GAN to do this nowcasting. Okay, so they are the pioneer in this. Okay, and then our breakthrough is in object-based nowcasting. Okay, object-based nowcasting. We start to work on it because of a joint project with UK Office. Okay, they want to do some nowcasting about convective storm. As I say, there's an increasing frequency of the kinds of storm in Europe and also in the UK. So in that project, that specific project, they chose us because there was a storm tracking algorithm we proposed in 2018, my student and I, and then they think this method is kind of quite applied. So they chose us to implement this method into their system. And also we further adopt object-based nowcasting model proposed in ROSI in 2016. It's based on common filter. Okay, so that's it. So basically, this method will try to identify convective cells, use current field time stable data, and then based on their track, you can extrapolate the potential movement of your rain cell. And if you use common filter, you can also come up with a kind of the uncertainty, the potential movement of these cells. Okay, and in this work, the main difference between us and the ROSI is ROSI they calibrate because you need to consider the uncertainty coming from the movement of your cell and how fast your uncertainty will grow. Okay, in ROSI's paper, they use pure engineering calibration of this parameter. And in our case, is we further analyze historical data, try to derive this uncertainty, how quick uncertainty will grow, and how to quantify it. So we based on more like the data-driven to derive this method instead of calibration. And in this work, we proved that by our way, the prediction is more informative. Okay. But you can see here, so there's no AI here. And then the second thing is we only consider the movement of the cell, okay? So a critical issue is here. Yes, we take care of the advection, but we didn't take care of the evolution. And in fact, in the literature, most of the object-based nowcasting method, they ignore the evolution, okay? However, but the thing is for convective storm, actually evolution is very, very critical because it usually happens in a very short time and then with a lot of energy. They are very unstable. So the property of the rain cell change very quick. They change in a very short time. But if we ignore that, actually our forecast skill decrease in a very, very short time. Okay, so that's where we found that AI may have a chance here to help with this. Okay, so we are actually inspired by this work. Okay, it's this work they kind of observe the physical process. Okay, how a single core convective cell the entire their life cycle. Okay, so you can see during this process. So you can see the whole life cycle of convective cell include three. They separate into three stages. The first one is called developing. Okay, your cells start to develop, and then it reach the mature stage, and finally dissipating, start to die. Okay, and then you can see during this process, there's a very important thing, is it form a convective core here, and then this core during developing time, this core start to forming and then start to get lift. Okay, start to get lift. Very quickly, it was pushed up, and then once it reached the mature process, it start to go down. Okay, start to go down slowly. Okay, and then eventually it disappear. So this work is inspired by this process. is we think the altitude of this convective core actually play a very critical role here. It could be a very good indicator to tell us the stage of your cell is in the mature stage or is in the developing stage. Because then based on that, you know if your intensity or your cell size is going to grow or not, or it's going to disappear, it's going to shrink. Okay, but in order to know this information, we need three-dimensional radar. Okay, we need three-dimensional. The original two-dimensional data cannot provide this kind of information. Okay, so here we develop a method that's the workflow. Okay, so this method we adopt. The first step, we try to reconstruct the cell lifespan in 3D. Okay, so we start from UKML office. They provide 3D their 3D radar image, and then so first thing is, but to track 3D is very complicated. So the first thing is we generate a 2D product from 3D. It's called VIL, the vertical integral liquid product. Okay, and from there we can apply the tracking algorithm we already have, so we can track the life cycle. And then after we identify the life cycle of our RAN cell, we go back to the original 3D radar to reconstruct the entire 3D cell. Okay, so from here we can reconstruct the entire 3D cell, how their life cycle change through the time. So through the 3D, we can find the altitude of our convective core. The altitude of our, that's the one we are looking for, because it potentially become a good indicator of the life, the property of your, how your property evolve during the life cycle. So we organize all this data, and then we put into an AI model. It's a very widely used standard AI model called LSTM. Okay, long short-term memory model is a recursive one. Okay, so this model has been used widely to do time series forecasting. Okay, so for each life cycle, how they evolve, how they change, basically is a time series. Okay, so that's why we train a LSTM model. So it's not any fancy model. It's a very widely used. I think many package you can find this model. So it's very easy to use. So so we use the evolution of property we track from 3D radar and then put into LCM model to train and help us to predict. Predict. So in this case, we use current and the path 3 time steps. So in total 4 time steps of the cell property as an input, and then to train and then to predict the next 3 time steps of our RAN cell, how their size change and how their mean intensity change. Okay, so we reconstruct and then we train the model. We also model the prediction error, but I'm not going to talk about these parts. So we focus on how property, how we nowcast the property. Okay, so here is the result coming from one single forecast. Okay, and then we try to separate it into different stage. Although I separate into developing, mature, dissipating stage, but the thing is, in LSTM model, we don't need to separate developing, or they can resolve this. Okay, so basically this result comes from a single LSTM. Okay, so LSTM, this model can distinguish developing, mature, and dissipating by itself. Okay, and then we try different combination of input here. Okay, so here first we can see this dark solid line is the ground truth. It's a ground truth. Okay, we look at the property of the major axis of your cell, the long one, and then the short one, and the minor axis. Okay, from these two we can derive the area of your cell, and also the mean intensity from only the 2D or from the entire 3D cell. Okay, so there's ground truth, and the dashed line is is to assume that if we don't consider evolution, so basically at this stage, if your RAN cell intensity is here, and then you only do the advection, then so it stays the same property. Okay, so that's kind of the reference we try to compare with is the operational one that didn't consider any evolution. Okay, and here we try different combination. Different combination, that means if we only use 2D property to do the prediction, or we use both 2D and 3D property. So here the 3D is the altitude of the competitive core that we track. And then, or we only use 3D, we only use the altitude from the competitive core. Okay, and we can find that for the geometry, so that means the long and the major and minor axis for the geometry of your cell, the area or the geometry, 2D is enough. Actually, when you consider 3D product, it doesn't help. It doesn't help. Okay, only 2D itself is enough to help you to predict that quite well. But in terms of intensity, 3D, that's core altitude is very, very important. It's very, very important. So that is a very good indicator to predict the evolution of your intensity. Okay. And then left-hand side is we have over like 2,000 cell life cycle, and then that's the overall result. Okay. So the dashed line again is the one if we don't consider any evolution, only the advection. And you can see from lead time 5 minutes, 10 minutes, 15 minutes. So the arrow just increased quickly. But however, if we consider evolution here, especially for the main interest is the intensity, is the green one is the one we consider 3D. You can see the arrow decrease a lot. And the most surprising is, although we only train to forecast the next 15 minutes, but if we continue to forecast continuous, although the arrows start to increase quickly, but still much lower than if you don't consider it. Okay, still much lower. Okay, so we can see that at 15 minute lead time, we can reduce the arrow up to 50%. Okay, 50%. So it's a very good. So it also shows that it's really, really important to account for the evolution for competitive nowcasting. Okay, so if you want to know more detail, we have this publication. You can have a look. I will leave the slides here, so you can, yeah. And then similar concept, we also use it to generate the life cycle of competitive cell here. That's more for the rainfall generator process. Okay, that's another work we recently accept. Okay, so the key takeaway from this work is, again, we to account for the evolution of rainfall is really critical. Is a key to improve the forecast skill of your model. Especially, it's very effective for competitive storm nowcasting. Okay, and also we show that it's not only the deep learning, it's also the advantage of using 3-dimensional radar data because you gain additional information to do that. And finally, it's important to understand the physical process of competitive life cycle. That's really important. That can help you to find really useful indicator in this case. Okay, so that's nowcasting part of work. And then another application is the climate risk modeling. It's climate risk modeling. Okay, so in climate risk modeling area, usually because we are trained as a civil engineer, so usually the area we work with is called catastrophe model. So we use historical data. We identify some statistical property from that, and then we use to design. But the implication here is we assume they are statistically stationary during this period. Okay, it may be okay to do this 20 years ago. Okay, but we know climate change, the speed of climate change increased a lot in the last 10 years. So we no longer can assume the stationarity of our data, of our rainfall. Okay, and then in this case, people with atmospheric science or meteorology background, they work with climate model. Okay, climate model can model these dynamics, this climate dynamics, this climate change. However, the resolution of these data are usually very coarse. And for our, for example, urban or for usual local, regional hydrological application, this resolution is not enough. It's not enough. Okay. So in this work, we try to see if we can fill this gap. If we can fill this gap, okay, try to incorporate the dynamics that's extract from the climate model, and then we can use it to affect our catastrophe modeling. Okay, so to do this, that's also one of the recent work we developed. So we try to explore, can we use analog method to help us to look into this? Okay, so before we look into this, for people who are not familiar with what is analog, basically you are looking for something similar from the past, and then you assume this the same thing will happen again. Okay, and so it's a widely used technique in climate or in weather forecast. For example, you may heard about weather typing or climate analog, this kind of method. So the traditional way is you find some key climate or weather variables, and usually related to rainfall, we look at temperature. We look at temperature. Okay, so for area, so you can see, and then you compare your current underlying weather, for example, temperature or pressure, geopotential height, several key variables, and then you go to historical data to see if you see something, to see if you can find something similar, and then so you can assume the similar situation is going to happen. Okay. And then the traditional way is to calculate a distance between them, Okay, so you compare pixel by pixel, and then you can come up with, so here concept is like a mean square error, that kind of concept. So when your distance is, or the difference is small, that means you are similar. Okay, so here we want to challenge is, we want to know if this is the best way to do this. Because our question is, first is you can distance, is this the best metrics to use? Is it the best metrics to use? Because you do pixel-wise, you are not really considering the spatial relationship between your pixel value. Okay? And also, if you have a little bit shift in space, the you can distance may result in very big difference, but actually they are not that different. Okay? That's a disadvantage of that. And another more critical issue is the current method you consider, temperature to temperature, pressure to pressure, humidity to humidity. So you compare everything independently. But is it really the best way to do this? Maybe there is a feature is 0.5 temperature plus 0.3 humidity, something like that. You get to something, the combination of them actually is a better indicator. Instead of the temperature, humidity, pressure, you compare them separately. Okay, so we want to look into these two. So we have these two questions we want to address in this work. Okay, so in order to do that, we use a deep learning technique to develop a very simple tool called climate dist. We call it climate dist. Okay, the concept is very easy. Okay, so we develop a network, two exact the same network. Okay, maybe easier. So it's like this. Okay, so it's like that. So in time, I randomly choose the weather or climate variable from random 2 time step. Okay. And then we try to extract some, because for deep learning or AI, the most common thing is called feature. Okay, we find a way to extract features. And this feature, the purpose is to help us to determine the time difference between these two. between these two weather. Okay, so this model is very easy because you know when you do AI method, usually the main challenge is to find your label. That's your target you want to learn. And in this case, it's very simple. Your label is the time difference. So you don't need to spend extra time to do the labeling. Okay, you just any time step, any 2 time step, you check feature, then that feature can help you to guess the time difference between these two. Okay, so that's how this model works. So the concept is very simple because it can identify the time difference. So we assume the feature you extract from this process indicate the climate dynamics. Okay, that are the features that can help you, can represent the climate dynamics. Okay, so we develop this model and then we train it. It can very well predict. So you just find any 2 time set as an input and it will tell you, okay, they are 11 months away, they are 6 months away. Okay, it shows very good performance here. Okay, and then here just to show results. So we use this method to help us to find analogs. To help us to find climate analogs here. And here to show that the blue one is to highlight our method as compared to some traditional method. And then we can see that in, for example, we can the analog we find, it can simultaneously find very good in terms of temperature, UV wind component, and also geopotential high. Okay, because the traditional method usually they tend to maybe find better temperature or better one of them, but from here we can find really good ones simultaneously for all the variables are interesting. And also you can see the correlation. Everything is much better than the traditional method or any other methods. Okay, so you can find the one that's really reproduce the climate, underlying climate. So we, but the thing is, if we just stay here, it's just a black box, because we're also interested in why this climatic model can find, what's the underlying mechanism it can find this difference. Because when we provide this data input, we didn't tell the model that this is come on November, this is come on October. No, it's just data. Okay, just data. But we find out that, okay, so we introduce, there's a method, there's some methods called explainable AI. Okay, it's an area. Many people propose different methods to help you to look into your AI model and then to help you to explain the result. Okay, so the right-hand side, there's a method called SHARP. Okay, I think this is a very widely used method. So basically, it's a method that's look into feature importance. Okay, so if you have different features, and it will show you which one is the most important one. So now it's a very popular method. You try many variables, and then you can do a SHARP value analysis, and then you can remove those not important one. So it's a very simple method. So here we can see that when we use SHARP value to look into the importance of this, and we can see actually there is a special distribution of the importance. Okay, because the traditional method didn't consider, it just assigned the same importance at each location. Okay, but actually because our target area, there's a mountain. So you can see in the mountain area, wind, the importance of wind start to increase. Okay, so you shouldn't treat it like in the ocean area. Okay, so there's a difference in space. Another thing is the method called LRP. So LRP look into a different layer inside your neural network. Okay, so analyze that your neural network from this layer go to next layer, how the flow goes, what the majority flow goes. Okay, it's called LRP, these techniques. And we found that in this specific area, first thing is, as I say, we didn't provide any like which it come from November or come from October. We didn't provide any this kind of information. But the model itself can distinguish, can gradually, according to data, it can distinguish the summertime and the winter time. Okay, they really can tell. And then it also tells us during summertime, actually we should look into temperature. During summertime, temperature is more critical for you to find good climate analogs. But in wintertime, the importance of U and V wind components become more critical. And in fact, this area actually has a predominant wind from the west to east during winter time. It's also you can see the data really reflect that truth, that the U wind in the winter time, the importance of wind, especially U wind, start to become critical. Okay, so that's also indicate that when we look for analogs, actually we also need to consider their spatial temporal difference. The traditional way didn't account for that. Okay, but in the deep learning AI model, they can flexibly consider this. Okay, so we further use this one to try to create a climate-dependent rainfall time series generator. Okay, so we because, for example, in the past, when we want to model, for example, rainfall from July, we probably go to all the historical July data to look for their statistical property, and then we used to create a like rainfall time series generation or modeling. Okay, but here it's different. For example, we want to look at current July. We go back to our history to look for the one with similar climate. We use climate model to help us to find the one really looks similar. Okay, so it could be in 5 years ago. It's actually from August. It's more similar to current July. Okay, so we can consider that. So we use that to model to help us to model rainfall. And so the traditional way will assume, all the, for example, here is from 2003 to 2008, all the June and all the July and all the August. Here, I just want to show that if we consider climate dynamics, their property is actually changed. It's actually changed with time. And also the original observation here we show is the skewness at 5-minute data. It changed at different year. But if this blue line it shows that if you use traditional method, use all the June data, it's a fixed value. It's a fixed value. You don't have that variation across different years. But if we use our method, for example, here the bit like green, the bluish way, we really have these dynamics. The most important thing is to see this event is in April 2007. There was a very extreme event. That April, you can see the temperature in that year, the April is much higher than any other April. Okay, it has some extreme event, and actually that year has very strong drought in this area, and we can see that. And if we use our method to find the rainfall analog, and here we show the skewness at 5 minutes. And we can see that if we use traditional method, that's the orange one, for different years, they stay the same because we use all the April. But we use our method. You can see in this 2007 picture, this very extreme event. Okay, and we can further use it to generate rainfall extreme like this. So rainfall extreme here is different return period, and if we only consider the traditional way, is the SBO, is a stationary way. It looks like this, but if we consider climate dynamics, we can show that actually there's much higher variability in terms of rainfall extreme. And also, if you consider, for example, 50-year return period, you can see the stationary one actually compared to the one we consider climate dynamics, it underestimate a lot. It underestimate. In majority of them, they underestimate the potential extreme rainfall. So here, just to demonstrate that this climate disk can be a useful tool to help you to evaluate the impact coming from climate dynamics. Okay, so finally, some conclusion about this part is it's a very useful tool, and also we use explainable AI to show that the importance from different climate variables, it actually change. It has a spatial temporal variability is in there. Traditional method cannot account for that. Okay, and I also see that climate dynamics has a quite great impact on rainfall extreme, and it's important that we should account for it. Otherwise, we may largely underestimate very high rainfall extreme. Okay, so that's it. So we covered a lot of topics here. Yes. Thank you.
Thank you, Li Pen. So we have time for questions.
I can ask. First question is very simple. How do you define rainfall process? What is it for you? I would not ask such silly.
You mean the null-casting part or the?
No, but in principle, what do you consider rainfall when you will try to, if you would try to make the real physical model of rainfall, what should be taken into account?
That's a very first, of course, the spatial temporal variability is definitely the key thing if your models want to represent the variation of rainfall.
But for example, over time, we do not have all this rain. Is the zero of rainfall? Is rainfall anyway?
You mean in intermittence?
Intermittence, heterogeneity, time and space. Okay, just.
That's actually one of the key challenges in you when you want to build a null-casting model. Yeah, because your data is very imbalanced. So that's actually constitute a very important thing. And that's first is you have a lot of zero. You have a lot of zero in your model. So if you don't consider this imbalance, this intermittency issue in rainfall, the model you generate will generate something really smooth, really smooth. So in our model, actually, we really especially I think it especially affect the field-based model a lot. So the key thing is how we sample data, so we can better model this process in AI model. That's always a challenge here.
I have another question about another part.
Yes.
Because for me, it's a little bit surprising, maybe contradictory, because you are looking for analogs in past for the climate, and at the same time, you are stating that there is dynamics. And if there is dynamics, you may have something quite different. How can you believe that you will find analog?
Yes, but that's always the limitation, to be honest. That's always a limitation of analog method. Because basically, you just cannot generate something that never happened before. Okay, but the thing here is we try to. There are several ways we try to do this. The first way is because before, when you are looking for, sometimes you are limited to calendar month concept. So in July, you only look at July. So statistics come from a very fixed man-made calendar month. So now we try to relax that. So we use a moving window. So hoping through moving window, you can maybe from mid-January to mid-February, you have something more similar. So that's one of the ways we try to do that. Okay, and then also the other way is, that's also, as I say, is maybe there are some dynamics you cannot directly see from temperature, humidity, those things separately. However, after you extract the features that can represent temporal dynamics, that's you can kind of reduce the impact from this. We also explore other methods, more regression-based method. So regression-based method is to so it can interpolate. So actually, it can also extrapolate some value. But we found that when we use that method, it didn't maintain the scaling relationship at different scales. So we're still looking for a way to better keep that. Yeah. So, but indeed, you are two really critical challenges here.
No,
yeah.
Because I don't know if a lot of people are saying when you're working with dynamics, you have to look rather for tendency. And this tendency will help you to understand how much will be different compared to the. And I did not feel it that it's here, so I was surprised because it's.
Yes. Yes. Yes.
Question regarding the polynomy, when you try to follow the manifold core,
yeah,
you have to define the threshold.
Yes.
Okay, you say okay, this core is defined because there are some specification.
Yeah.
And so, how do you define this?
We actually was sensitivity analysis. In the end, we use 85% percentile. So the top 85%.
To see.
Sorry.
This threshold has an influence on the modeling.
Yes, because if you use a too low percentile, it's not accurate to really find the core. But practical issue, for example, if you use 95 percentile, it's too extreme, it's too strict, and then you may not find a very reliable. Maybe you only have very few pixels to help you to identify that altitude. So it was really a sensitivity analysis, and then we found that 85 percentile give us just the best result. We have enough pixels to help you to really get the reliable estimate of the height of our core. Yeah.
Use methodology to compute some deterministic classic.
Sorry?
You use this methodology to compute some deterministic.
Actually, also stochastic.
Okay.
Also stochastic. The part I didn't cover here is the error modeling. So the error modeling is a part for example, we forecast this property, but we can perturbate some potential way. Actually, it works quite well. Yeah. It helps to consider the uncertainty coming from this evolution.
Yangzi, if you have a question.
Yes. Yes, thanks to Professor Wang to give this presentation. I'm quite interested in the part of explainable AI because you have mentioned about one method is called shape, and if I understand well, it's a method for explain the AI model, which in indicating which feature is more predominant in your modeling. And in your study, I would like to ask, you applied this method, you applied shape in your training data set, or you use it to explain the result in your testing set?
It's in the testing set. So this result come from the testing set.
Okay, so you basically just to see which for example, in your case, temperature or wind is more important, predominant in your fields. It's not when you training the model, you found that for example, the temperature is not important and remove that feature.
Yes, but actually here it's more like we didn't really remove, but if we choose to remove, we'll probably remove the potential. It didn't help that much. Yeah.
Okay.
Yeah, and but you can see is we calculate that at every pixel locations. So you can see at different pixel at different locations the relative importance between different variable change.
Okay, I see. So this importance is variable in space.
Yes, and then you can see actually when there's a mountain area, the UV wind become very. Here's a mountain area in the lower right corner, and they become more important. Yeah.
Okay, I understand. Thank you so much.
Okay.
Yeah, you mentioned at the beginning that the question of scales was very important,
Yes.
but I didn't see so much this question after that.
Yeah.
Especially I have a case, one of your slides, it's about the skewness.
Oh, yes. This one, skewness. Yeah, it's all skewness. Yeah.
The funny thing is that skewness is scale depending.
It's sorry.
Scale depending.
Yeah, it is.
So,
it is.
Yeah, it is.
No, actually, here I just show 5 minute one, but actually in this model we have 5 minute, 1 hour, 6 hour, 1 day. We look at different scales. But here I only show the 5 minute one. Yeah.
What did you extract from the fact there was some scaling dependence for the skewness? What did you do with it?
But in this method, we it's in the downstream application. So we find the analog, and then we use those analog the corresponding rainfall time series for that period, and then we extract moment. We extract statistical property at different scales on that moment to build our rainfall generator. Yeah, I think you probably know it's a Bartlett-Lewis one. I'm not sure you're happy with that, but in this part we link to a Bartlett-Lewis model. Yeah, but the thing is, the analog actually can be independent from the generator you want to put together.
Yeah, but that's very important. The analog will be not the same according to the different scale.
Yes, actually that's a good point. But the thing is, because analog when you use actually when you are in the neural network this process, I didn't show the detail here. It applies several convolution, and here convolution is different from the mathematical convolution. The convolution in image processing is a bit like aggregation. Okay, so basically during this process I didn't show here is it will apply several convolution to look at the climate variables feature at different spatial scale, and then so one from one time point and another one from another time point. So these two actually they compare climate variable at different spatial scales, and then help us to predict their time difference. Okay, so I didn't explain this part, but actually the spatial temporal coming from climate variables are considered during this process, because in AI applications, when they apply to like nowcasting or many variables, actually the convolution is really a very important thing, and convolution is all about spatial scales. So indeed, yes, I should have shown the detail of this network, because it really indicates they are looking at different spatial scales. Yeah, from two different time variables, and it helps a lot to predict their time difference.
Not very satisfied.
Okay. Yes.
Okay, I have one
Yes.
question. Which metrics are you using to compare your nowcasting with the existing field?
You mean the field one?
Yes. How do you validate the nowcasting?
Here of course, here I only show more like a visual comparison, but I can share with you. There's a manuscript. So we compare several steps. One is the standard like MAE or MSE, that kind of square. But we also consider the I forgot the RSPP or something. I forgot the name. Is to compare the spatial structure. Yeah, based on the Fourier transform. Yeah. So we also consider that. So we can tell that when we consider when you use the DGMR with a GAN framework, it maintains more details in high resolution, small scales. So we compare at different the overall prediction performance, and also if they can reconstruct the spatial the spatial pattern.
Some other questions? Okay, thank you. We'll
Thank
stop
you.
here. Thanks a lot. And we'll stop.
So anyone, I just remind that anyone is invited to go to our meeting. These 434.
Thank you.